So the question of the day is, what makes a strong acid strong and a weak acid weak? There are several things that we know about strong acids and weak acids. One is how well they conduct electricity. I have some concentrated acetic acid in this flask, and I'm going to put it into this beaker. Inside the beaker there are two electrodes. When those electrodes are connected, the light will turn on. Let's see how well the acetic acid does. Not very well. In fact, it's so dim I can't even really see it in the light of the room. So not much light there. Not much in the way of electrolytes happening. So because of its poor showing, we can see that acetic acid, even in its concentrated state, is still known as a weak acid. Let's compare that to hydrochloric acid, which is known as being a strong acid. Here we go. Hydrochloric acid, and wow, it's easy to see the light in this case. The electrons are having no trouble getting from one electrode to the other. So there's a great deal of electrolytic activity in the hydrochloric acid, and yes, it is considered a strong acid. So the reason why HCl is a strong acid and acetic acid is a weak acid has to do with their ionization. How well they break apart, they dissociate into ions. For HCl, it does it extremely well. In fact, when we show our equation for HCl breaking apart to form ions, we see that there's really only a solid arrow going to the right, because this HCl, well, almost all of it makes products. On the other hand, when we see acetic acid going into water, we do see the formation of hydronium ion and what we call the acetate ion, the acetic acid without the hydrogen on the end. But notice that there is a reverse reaction. In fact, there's more of a reverse reaction than there is a forward reaction. For HCl, it's almost all forward reaction. So again, hydrochloric acid does a better job of dissociating, breaking apart into ions than acetic acid does. And when it does that, it enables electrons to flow more freely. Thus, its strength of acidity. Now, let's think in terms of the Bronsted-Lowry model for a second. The reason why we have only one direction here is because this conjugate base is too weak of a base to react and try to take away that hydrogen ion from the water. So the water wins. So that's why it stays on this side. It's like a back and forth, but in this case, this guy's too weak. Oh, I can't push it back to the left. I'm just too weak. But the water's like, oh, push it to the right. And he pushes it to the right. And so here we are on this side with nothing in the way of a reverse reaction, really. On the other hand, acetic acid. The acetate ion that came from the acetic acid is a strong conjugate base, stronger than water is. And therefore, the conjugate base can take that hydrogen ion back and push this reaction to the left. And because of that, we actually have more of these than we do of these. Oh, that sounds familiar. I think we talked about this in equilibrium, didn't we? Where you have a ratio of concentration of products over reactants. That's right. We have K values for acids and we have them for bases as well. So let's talk about how to figure those. So you remember how we solve for K, the equilibrium constant of a reaction? Remember, we take the concentration of the products over the concentration of the reactants. So we do that for these acid reactions, these acid-base reactions. Here's the KEQ for HCl. Notice we have hydronium ion concentration multiplied by chloride ion concentration divided by the water concentration and the concentration of HCl. But remember, water is a pure substance, right? And what we do with pure substances, we don't use them in our equilibrium expression. So, we simply have the concentration of hydronium times the concentration of chloride over the concentration of hydrochloric acid at equilibrium. The same can be said with our reaction with acetic acid. The KEQ would be the acetate ion multiplied by the hydronium ion over the reactants, water, but again, we could take that out, multiplied by acetic acid. So these represent our equilibrium constant expressions for these reactions. Now, one more thing. Because this is an acid, we do a special little thing with these equilibrium constants. Instead of calling them KEQ, we call them Ka, the acid dissociation constant. That is to say, how well that acid dissociates in water, breaks apart to form ions in water. I told you before we have strong acids and weak acids. Let's illustrate this with the Ka values for these two respective acids. The Ka value of HCl is 1.3 million. Wow, 1.3 million. In other words, we have way more products than we do reactants. That means that this thing pretty much totally ionizes to form the products of hydronium and chloride ions. Meanwhile, the Ka of acetic acid is 1.8 times 10 to the negative fifth. Very small. And remember what we said. Anything above 1 constitutes a product favored reaction, or in this case, a strong acid. So anything over 1, a Ka greater than 1, is a strong acid. It has the ability to make those ionized products more so than the leftover reactants. But for a Ka of less than 1, we consider that to be a weak acid. So yes, acetic acid is a weak acid and HCl is a strong acid, and we can confirm this based on the Ka values of each one. Strong bases like NaOH, sodium hydroxide, dissociate completely in water. Because of that, we only show the arrow pointing to the right. Basically, we have all products here and no reactants left over. Very high Kb. Here is an example of a weak base. This is methylamine, a weak base. It reacts with H2O, and it has a two-way reaction, doesn't it? We can see that the conjugate acid is here, the conjugate base is here. Now, the reason why that methylamine is seen as being so weak is because of this guy right here. This is the hydroxide ion, and as a conjugate base, it's actually considerably stronger than the methylamine is. So therefore, it keeps pushing everything back toward the left. Because of that, we have a great deal more reactants than we do products. And the Kb illustrates this. Yes, you heard right. Kb, the base dissociation constant, how well a base ionizes in water. The Kb in this case is figured in the same way that we figured the Ka. We have the concentration of CH3NH3 times the concentration of OH over the concentration of CH3NH2. Our products over our reactant. Again, remember, we don't have to include water in this. And that's how you find the Kb expression for a weak base situation. Okay, got a problem for you. Now, you want to go back like 30 seconds and see what was written on the board right here, because that'll help you out a little bit. It was the Kb expression for this equation. Remember, products over reactants. Here's what I want you to do. Let's say we have this reaction, and at equilibrium, the concentration of CH3NH2 is 0.15 molar. The Kb for this reaction is 4.3 times 10 to the negative 4. Now, remember, for every one of these, we get one of each of these, right? So these concentrations are equal. That's your hint, okay? These concentrations are equal. So I want you to solve for the concentration of OH ion if the concentration of CH3NH2 at equilibrium is 0.15 when the Kb is 4.3 times 10 to the negative fourth. I know, but I think you can do it, okay? Give it a shot. Okay, that's all we're doing for today. Remember, we talked about strong acids and weak acids, and strong bases and weak bases. Strong acids are those that dissociate completely, as do strong bases. They dissociate completely in water, and because of that, they allow for a great flow of electrons. They're very electrolytic. Also, we said that their K values are greater than 1. They have more products than reactants, more dissociated ions in that solution than there are undissociated molecules. We also talked about how you can find the Ka or Kb, how you can write the expression for both of those based on a reaction like this, where it's products over reactants. And we said as a reminder that K values that are greater than 1 represent something that's strong. Whether it's an acid or a base, it means that it dissociates, it has greater amounts of products than reactants. And so a K value of less than 1 represents something that's weak, something like acetic acid or methylamine in this case. All right, guys, I hope it's been informative to you. Again, let me know if I can help you in any way, and I'll be happy to do it. Until next time, God bless.